for producing binary 1. In dynamic logic circuit, only pull-down network or only pull-up network will be present. In this lecture, we are going to concentrate on CMOS static combinational circuit, this one. To implement this circuit, we need N transistor here, N transistor here, and twice N, if the number of input is N. To implement dynamic circuit, we need N number for the pull down or pull up plus 2 clock transistor. So the number of transistor we need for dynamic circuit is N plus 2, N being the input. So for N input, we need twice N for static, N plus 2 for dynamic. Each one has its own pros and cons, but just looking at this number itself, we can see that, let's say you are given a 10 input circuit to implement, N is equal to 10. Here, to implement the same logic function using static style, you need 20 transistors. Using dynamic style, you need 12 transistors, almost 50% savings. So in terms of space you need on the chip to implement the function, dynamic style will be a huge savings. Less transistor, less power, less area. So, but later we will see that from robustness point of view, from performance point of view, static circuit has some. From robustness point of view, static circuit has some advantage. On the other hand, from energy efficiency point of view or area point of view, dynamic circuit will have some advantage. We will discuss those in detail. Now let us concentrate on static CMOS circuit, combinational type. So as we mentioned earlier, this circuit is made of two complementary or dual networks based on duality principle. Pull-down network is made of NMOS, pull-up network is made of PMOS. So this duality network also extends to its duality principle to the connection. So there will be exact same number of inputs going into the pull-down and pull-up network. So the number of transistors here and the number of transistors here will be equal, but they're opposite type, NMOS and PMOS. Their connections also opposite. If you have two inputs A and B, if let's say the connections from A and B will be connected to pull-down network, if those two corresponding transistors in the pull-down network corresponding to A and B, they are in series here, they will appear in parallel in pull-up network. If they appear in parallel here, same two transistors will appear in series here. So these two networks, they are complementary or dual to each other in every sense. One is pull-down, binary produce binary 0. Other one is pull-up, produce binary 1. One is made of NMOS, the other one is made of PMOS. One is connected to ground, the other one is connected to supply. Any series connection here will become parallel over there. Any parallel connection here will become series over there. Connections also will be same. So all you need to learn is to how to construct pull-down network. If you know how to construct pull-down network, then automatically you know how to construct pull-up network. You draw the exact same circuit, just flip the transistor, flip the connection. So if you know how to construct a pull-down network for any CMOS circuit, you actually know 100% of the static and dynamic circuit design. So we are going to go slow at the beginning, how to implement a pull-down network, and then we'll go from there. So typically in NMOS network, that is the pull-down network, whenever we implement any AND operation, the transistors will appear in series. If you see a series connection of three transistors like this in any pull-down network, if it is pull-down network, this has to be NMOS, and A, B, and C. The term you are actually implementing is A and B and C. So if transistor appears in series in pull-down network, there is an AND operation. If the transistors appear in parallel between ground and output here, in the pull-down network, same ABC, if they appear in parallel in the pull-down network, the term you will be implementing is A plus B plus C, OR term. So all you need to remember, in pull-down network, series for AND, parallel for OR. Then everything else will be complementary. And there is a reason why series is chosen for AND in pull down and parallel is chosen for OR in pull down. And then since PMOS is complementary, in PMOS if they appear in parallel, 3 PMOS appears in parallel, then it is an AND. If they appear in series in PMOS network, then it is OR. Complementary, dual of pull-down network. So why is like that? So, but again, always look to this slide, the classification, different classification of logic circuit. We are talking about combinational, static, and CMOS circuit. So now let us go deep into this construction of pull-down and pull-up network. So now, let's say this is I and output signal Y. This is an input signal X. When I can make Y equal to X, if I can establish a connection from X to Y, both signal will become equal. So Y is equal to X. It will be true if both A and B are on, they are in series. So if A transistor is on, B transistor is on, we have a series of 2 NMOS transistors. If A and B both are on, both are high, this NMOS transistor will be on, X will be connected to Y, then Y will become equal to X. On the other hand, if I connect same 2 NMOS transistor in parallel, A parallel to B, this side Y, this side X, I can make Y equal to X if X gets a connection either through this one or through this one or through both. In this case, Y will be equal to X if A or B or both are high. There is no if, but minimum, at a minimum, you can just turn on one of them, then Y will be connected to X. So that's so now series giving us an logical AND. It is becoming equal to X when both of them are on. It is becoming equal to X when one of them is on. So this is OR, that is AND. Now the question is, the X will be the one who will be determining Y value. It can be ground or it can be supply. This X can be ground or supply. But when we are talking about NMOS transistor, and we are setting the output Y. So we want to, next time $10 per entry. So this will be connected to ground. We always know that the bottom side of the pull down network and NMOS network is connected to ground. So here, first I am giving you the information why series is for AND, parallel is for OR. But then let us look at the actual reality of an NMOS network, pull down network. This node will set the value of the output, and we know that in a pull down network, this side is connected to ground. So Y will be equal to X, that means 0, when A and B equal to 1. Right? In this case, both A and B, if they are 1, first case, if A and B both are equal to 1, then Y will be equal to X. In case of pull down network, it will be 0. If A equal to 1 or B equal to 1, in the second case, Y will be equal to X, which will be 0. But in a truth table and truth table, let's write and truth table, right? How many different combinations we can have? 0, 0, 0, 1, 1, 0, 1, 1. In an AND gate, 0, 0 means 0, 0, 1 means 0, 1, 0 means 0, 1, 1 means 1. Right? But so only 1, 1 combination will give 1 at the output. But here, the series connection of two NMOS transistor is giving us what? Forget about the parallel one for the big. When A equal to and B equal to both are 1, X equal to 0. But if A equal to 1, B equal to 0, Y is not 0 because it is not connected. It will be floating. So if it is initially high, it will remain high. On the same thing, if A equal 0, B equal 1, one of the two series transistor is off, so Y is disconnected from X, which is ground. So here, Y is 1. So what I am getting here is actually, by connecting these two transistors in series, the actual Y I am getting is 1, 1, 1, 0. While I am trying to implement an AND operation, what I am actually getting? I am getting actually AND operation, I am getting a NAND. So CMOS, so now I am introducing a basic properties of CMOS circuit. CMOS circuits are by default inverting in nature. When you are trying to implement an AND function, it will give you a NAND function. When you are trying to implement an OR function, it will give you a NOR function, opposite of what you are trying to do. So if you want OR, what do you have to do? First, you have to implement NOR and put an inverter. Because what is the difference between OR and NOR? Is, let's say this is a symbol of OR gate, right?
NOR is just an inversion. Yeah.
This is a symbol of OR gate. An OR gate followed by an inverter is a
NOR gate.
NOR gate. Or if I put this one, this is a NOR gate, right? A NOR gate followed by an inverter is an OR gate. So this is the symbol of NOR. So if you implement following this style, series for AND, parallel for OR, in pull-down network, actually instead of getting an OR, you will be getting an OR. Similarly, this is NAND, this is AND. By default, you will be getting NAND operation, so you have to put an extra inverter at the end to get AND operation. So CMOS, any CMOS circuit, CMOS logic circuit, they are inverting by nature. For all ones, it is giving us 0.
But why it is giving us 0 for one? Both the transistors are in series, right? So both are on. So output should be
Because
one, right?
this is, we're talking about pull down network. If this is output, think about the pull down network. One side of the output, one side of the pull down network is connected to output. I am calling it Y node. What is the other side? Ground. So when the pull down network is on, that series path is on, output is getting connection to where? Ground. So for A equal 1, B equal to 1, then series transistor is on and it is establishing a connection from output node Y to the ground node X. In this case, I'm generalizing it node X. Now, theoretically, I can put this series connection. The reason I didn't write ground here, now I'm explaining why. Theoretically, I can put a series connection of two transistor, NMOS transistor in pull-up network to implement same AND or NAND function. Theoretically, I can do that. The series connection between X equal to VDD now, not ground, because I'm talking pull-up network. So what will happen? When I turn on A and B by making it 1 and 1, if it is VDD, that means binary 1, will travel from X to Y to make them equal. But what will happen? NMOS is a bad pull-up device. As it passes from here to here, by the time it reaches here, it will experience one threshold voltage drop here. Then again it passes from here to here, it will experience another threshold voltage drop here. So NMOS is not good pull-up device. So same series of, so series for AND, parallel for OR. First, establish that in your head. Why? Just connection itself. To establish the connection, forget about it's a ground or VDD. To establish the connection from Y to X, I have to turn on both A and B, right? Because they are in series. So series connection will give you AND operation. Here I can turn on both. I'm relating with my statement to the circuit. A or B can be turned on to make Y equal to X. So parallel for OR, series for AND. But this, to implement this series AND connection, AND operation, I can take it, I can put it in the pull-down network, but I can put it in the pull-up network. If I put series of two NMOS in the pull-down network, the connection on the other side, it will become a ground connection, so it will produce a perfect binary 0. But if I put it in the pull-up network, then this becomes my VDD, and NMOS is not very good pull-up device. So theoretically, we can produce an uninverted AND gate. We are always getting NAND gate, not AND gate. Why? Because then we will be sacrificing integrity of the signal. That signal will be distorted. What if there are 4 NMOS transistors in series? So you will be having 4 threshold voltage drop. By the time it reaches output, your signal will be in undefined region. So that's why we put this in series in NMOS in a pull-down network. Now, we can now look at the same thing. A series of 2 PMOS transistors. A series of 2 PMOS transistors. What function it is we are implementing? Y will be equal to X when both this PMOS and this PMOS are on. For this to be on, A should be 0, B should be 0. So I am implementing an AND operation of A bar and B bar. Right? If A is true, means A is 1, then A bar will be 0. Right? If B is 1 or true, that means B bar has to be 0. So this is if A bar is 1, B bar is 1, that means A is 0, B is 0, only then Y equal to X. So it is a series connection of two PMOS transistors giving us operation of A bar and B bar. De Morgan's theorem. A bar and B bar is equal to A plus B whole bar, which is a NOR function. Now we can put these two PMOS transistors in parallel, do the same thing. It's an OR operation of A bar or B bar. De Morgan's theorem. A bar or B bar is AB whole bar, which is a NAND operation. So now, let us go back. A series of two NMOS transistors in pull-down network will give me AB NAND. Parallel of two NMOS transistors in pull-down network will give me AB NOR. Opposite of inverted of OR. And if PMOS transistor appear in series in pull-up network, it will give me a NOR, opposite of this one. And if they appear in parallel in PMOS, it will give me a NAND. So, by direct implementation of this series and parallel connection, you will be getting NAND and NOR. All you have to remember, for AND NAND, NMOS transistor will appear in series in the pull-down network, in parallel in the pull-up network. For OR NOR operation, NMOS transistor will appear in parallel in the pull-down network, and corresponding PMOS transistor will appear in series in the pull-up network. Right? So this all you have to remember. Now again, the reason we choose this series connection for pull-up network, because PMOS is good, and put it in the pull-up network because PMOS is good at pulling up. So just remember these two slides, series and parallel, series and parallel. So now let us randomly, before even proceeding further, randomly implement this function here. Forget about OR. So the function you are going to implement in any CMOS circuit, after you implement it, it will always appear in inverted form. So if you are given to a function y to implement, the end result of the circuit you will get, it will be y inverted, y bar. So now, let us look at this function, ABC, AC bar B plus ABC, AB bar C. First step, when you are given to implement, tasked to implement any such logic function, the very first step you have to see, can you simplify this logic function? Because this term has 3 inputs. This term has 3 inputs. This term has 3 inputs. So to implement each one of them, you need 3 transistors here, 3 transistors here, 3 transistors here, 9 transistors, right? They are in OR operation, they should be in parallel. Inside this, they will appear in series. for pull down network. These three will appear in series, these three will appear in series. These three are in OR operation. So these three will be in parallel with these three, will be in parallel with these three. Altogether 9 transistors. And then you need an inverter to invert this, you need another inverter to invert this. So 2 transistors here, 2 transistors here. 4. So 9 plus 3, if you do not do any modification, your pull down network itself will need 13 transistors. Right? But you as the VLSI designer, your first job is to find the simplest possible logic function to express the same thing. What do you mean by simplest possible logic function? Can I minimize the number of terms? And can I minimize the number of literals or variables in each term? So, I intentionally gave this just simply doing a Boolean algebra. Here, A and B both are uninverted. So I can take AB common, C plus C bar, here AB bar C. C plus C bar in Boolean function is what? 1. So I have now same function AB plus AB bar C. So this is much simpler. So now we are going to implement this. So now it will be much easier for you to implement. Yes.
I have a question regarding the PMOS and the NMOS and the PMOS.
Yes.
So you, in the previous one, if we connect in series, it's AND function?
AND or NAND, yeah.
AND or
NAND.
NAND.
Or NAND is inverted form of AND. So
okay, got it.
yeah.
Got it.
So
I
now
got it.
let us look at this. We have, so for Y function we want to implement the complete CMOS circuit. So the first term is A and B AND operation. So I will have one branch with ground, and this will be my output Y, and this branch is A and B uninverted, right? And parallel to it, because it's OR, this whole term is in parallel to this term. So they are in OR operation, right? They are in OR operation. So in that term, what I have 1, 2, 3 transistors. A will go as an uninverted form, B will be an inverted form, and C, right? So I have my complete pull-down network for this function, following the principles of these two slides. Now from here, I have to now construct the pull-up network. Series will become parallel, NMOS will become PMOS, parallel will become series. So this whole block will be in series with this block, because here they are in parallel, right? This AB block is in series with AB prime C block. In pull-up network, this block will be in series here. Internally, they will be parallel. So now my first block will be, let's draw parallel 2 transistor, right? This will be now PMOS A, PMOS B, right? And then this whole block will be in series with a block of 3 parallel transistors. And all these transistors will be PMOS. Just a minute, let me finish this. and then this block will be connected to VDD. This side is common ground, right? So now, but we said that when we are trying to implement any CMOS function, whatever we implement, we are implementing AND OR terms, but the final result we will be actually getting the inverted version of the function we are given to implement, because it is by default implementing, because when these values are high, one of the path will be on, it will be low. If these values are low, input values are low, one of these path will be on, it will be high. So by default, any CMOS circuit will be inverted. So you are given to implement Y, the output you will be getting, that will be actually Y bar. So if the question is, draw the circuit exactly to implement Y, so what do you have to do? Put an inverter here. This is your Y, this is your Y bar. Directly the output of the circuit itself is Y bar, this will be Y. Yes, go ahead.
So I have a question. So first we are drawing the down one, that is the NMOS.
Yeah.
Then we are drawing the
You
PMOS.
actually can go, if you start with slide 4, the slide 8, you can actually start drawing this. All you have to remember, in case of, we are just dividing into two groups, NAND or not. For this one, series in PDN, parallel in pull-up network. If you remember this, if you start from here and here, it doesn't matter. You can do the top one first. Easier to typically, NMOS pull-down network is more frequently used than pull-up network. Pull-up network is PMOS is larger. Like dynamic circuit can be implemented both using PMOS network, pull-up network, or pull-down network. But since pull-up network is made of PMOS, they are slower, they are larger. Almost 99% of the dynamic circuit is implemented using pull-down network only. That's why I always start with pull-up. But you can remember in any way you want. Everything you have to just remember here. For or not, parallel in the pull-down network, series in the pull-up network. If you remember that, then any you can implement it. Yes.
This one used to right here is static, right? You got
This is static.
Pull down and then the pull up.
Yeah,
If
yeah.
you just did like dynamic, you would just have one of those sides.
Yes. Actually, that is our lecture 5, but it's a good question. Let me draw the two versions of dynamic circuit. One is called N-type dynamic circuit, and this is pull-down network. There is another clock here. This is clock transistor. This is clock transistor. This is my output Y. This is VDD. This is ground. And here the N input. So if for the same logic function, if the question is, this is static CMOS, if I draw only this part instead of ground, put a clock here, connect it to ground, delete the entire pull-up network, put a clock here, connect it to VDD, that becomes my N-type dynamic CMOS.
Which you said is the most common.
Yeah, in case of dynamic circuit. But there is another version of dynamic circuit, that is pull-up network. There will be a clock. This is ground. There will be a clock. Output is here. This is my output. So this is called P-type dynamic. So now we are jumping ahead on lecture 5. If we compare P-type, N-type dynamic versus P-type dynamic, this one will consume almost 2 to 3 times more area, because for equivalent speed and resistance, NMOS transistors are much smaller than PMOS transistors. In terms of circuit complexity and connection wise, they are almost exactly identical. Same number of transistors, same number of connections, but this one will be made of NMOS, this one will be made of PMOS, so that will consume higher area. So now, for the same logic function, if your question is definitely a midterm question, because the midterm question is ready, definitely you will be given a logic function. Question is out. You will be given a logic function like this, much more complex than this. The first step, simplify it. And then you will be asked to implement static CMOS version, P-type dynamic version, N-type dynamic version, and then few other types of circuit we are going to discuss in next couple of lectures.
But if we are actually applying an inverter after it, it's better we invert the input signal initially.
It depends on the, if you want to invert everything here, then you need 1, 2, 3, 4, 5, so many inverters. So sometimes it actually depends on the function, but sometimes to trick you, what I can do, if I give this like this, then you don't need this, right? Or I can give a function like this, whole function is inverted. Forget about this for the time being, simplify it, then this is for your end result. So your y is actually the inverted version of the function. So then if you implement this one, then you don't need this inverter anymore because your y is here. So look at this whole bar here or here. But if it is like this, as it is, then when you implement this one or this one, the output will you get is an inverted form.
And if you are good in algebra, you can reduce it and
Oh
reduce
yeah,
it.
yeah. So that's why when I give you at least the exam minimum 16 variable problem. This is only 9. Each one of you will stop at step 2 and 3 in simplification. One of you probably will go down to make it like only 5 variable. Some of you will stop at 9 variable. Some of you will stop at 7 variable, depending on how good you are in. Sometime when you are looking at a complex logic function, you can immediately see which two terms can be joined together to make it smaller. Depending on which permutation combination of terms you are putting together, you may end up different types of, each one logically same function but different complexity. Yes?
Do you mean 16 terms or 16 different input signals?
No, that's it can be made. I'm giving the close information. So let's say something like that. So 4 variable each, 4 terms. That can be total.
So we can still use it.
No.
Huh?
So
Oh
we can
yeah,
still use
yeah,
it.
yeah.
It will be too big.
4 variables, 4 terms, it's not that going to be that complex. Don't worry about it. You can, the expression, definitely I don't expect that you are going to implement that 16 variable problem directly as it is. Then what you will end up, series of 4 transistors, 4 in parallel, 4 branches in parallel, right? And then on the top side you will have parallel of 4 blocks in series, right? So, yeah, definitely you have to simplify the expression.
My question is related to this math. So why in the NMOS, sorry, the PMOS, you have drawn the first A and B, then A, B,
Yeah.
then after that you drawn that
Okay,
circuit.
that's
Why?
actually-
What's the reason?
Okay, there is no reason because when they are in series, logically, but this is actually a very good observation. Smart designer, depending on the signal activity, if you put this block here and this block here, let's call this block as my P block, this block as my Q block, just for simplicity. They are in series. P in series with Q block, V2 in output Y and VDD. Logically, if I do this, if I swap this block,
Same result.
function, logically there will not be any difference. So you can, at this point, you can basically, but by the end of the lecture 4, you will see that not only you have to simplify, and you have to make a smart decision, should I put this block with the output or with the VDD? Because logically, since they are in series, ultimately it will give you the same logic function. It doesn't matter whether you put this block closer to output or closer to VDD. But actually the practical design consideration, depending on the nature of these A, B, C, D inputs, you will see that it will make a huge difference in terms of performance. Both options will give you the correct logic value, but one will be delayed compared to the other. So that's what we are going to discuss.
That's why I was asking. In the bachelor, I did the delayed one.
Yeah. So we will talk about it why.
Last question.
Yes.
You
No,
put-
you can ask as many questions as you want.
Okay, you put directly the over there, the not the NOT gate. We need to inverse it, right? The Y, the inverted gate.
Yeah. So at this point, because this one I drew for this up, so this will be an inverter.
Yes.
This is Y bar. This
Do
is
we
Y.
need to actually draw the circuit, not the NOT gate? Like
So
in
if-
the
So
example.
again, that's another good question. If the answer is for this given expression, implement Y. Don't make sure that you don't miss this inverter. Because if you finish drawing here, you have implemented actually Y bar.
Yes.
But I want you to implement Y. So you have to make sure that
We need to inverse it. What I'm saying is you have directly put the triangle. Do we need to put the actual circuit like NMOS and PMOS?
Yeah. He
For-
wanted to say two
okay,
transistors
so
in
no, I understand what you're saying. So do I need to basically draw the circuit? Because you already know it's a single inverter. I will not penalize you if you draw like this or draw the actual inverter circuit.
That's what I was asking.
Yeah, but in actual circuit simulation, if you want to put this into a SPICE, you have to draw every single circuit.
Circuits, yeah.
So, but to summarize, so what we have, pull up is the dual of pull down. Duality, and it comes from De Morgan's theorem as well. A plus B whole bar is A bar and B bar. A B bar and whole bar is, so that's duality principle where, right? So, as I mentioned, actually directly we're implementing a NAND gate, but if we want to have an AND gate, we have to add an inverter. We will get an NOR gate, so we have to put an inverter if we get an OR operation. Because by default, it is inverted.
One
Yes.
similar question on that note. Are you going to want us to include the inverter for the input signal, like B naught, or do you just want us to?
No,
maintain-
you just have, because by this time, you and I all both know, I have to pass it to an inverter. But if the question is, how many transistors you need to implement Y? Then, no, you don't have to draw, but let's count. 1, 2, 3, 4, 5 here, 5 and 5, 2 n. Simple 10. But I need this inverted, right? And somewhere I deleted, oh sorry, only one inverter here, right? So 2 transistor here, 10 plus 2 plus 2.
Plus
14
another
transistor. Oh, there is another here, yeah. So you have to, every time, every place you need an inverted signal, count 2 transistors for that. So you are getting all the question out by asking those questions. But that's a good question. You have to count this. Whether you draw the inverter or not, it doesn't matter. As long as you put the time sign or bar sign, that's good.
We don't need to draw the inverter like.
No, there because I don't want, I know that
This will-
he has to go with, but when the transistor count question comes, you have to make sure that you count these 2 transistors.
Into 2 Wait, there will be 3 transistor, right?
Why 3 transistors?
So, oh no, the 2
This
transistor.
is already counted, 1, 2, 3, it's a 5, now we have what we have, we have a 5 input function. So 5 here, 5 here, for pull up and pull down network, 10, but then count how many inverters including this one you need.
Oh, that's true. We would only need 14 because that input we
Yeah.
we could
Yeah,
invert the
because
input
this
before it
B
goes into the
inverted,
network.
it is not that you are applying B twice.
Right,
The inputs are all coming here,
right.
A, B, C. If we need B as an inverted form, so what
We need to
have, put
Inverted.
that here. So here I have A, B, B prime, and C available. So I will just draw the connection wherever needed. I just avoided running all the wire, right? So if you need 2 transistor, invert one inverter to invert B, that's it. You don't need to repeat it here because these are common inputs, right? Going to go pull up network and pull down network. It's not that you are separately applying to pull up and pull down network.
So how many over there?
Yeah, so how many total?
14.
So here, 5 here, 5 here, 10, 2 for inverting B, 2 for inverting output, 14. Because here I am getting Y bar, right? So to get Y as it is, uninverted, I need an inverter over there. So now this slide should be very easy. If I want to implement a 2 input NAND gate, NAND is what? AB whole bar, right? So A and B will appear in series in NMOS pull down network. They will appear in parallel in pull up network. So this is NAND of A and B. I don't have to do anything because by default CMOS gates will give me NAND and NOR, right? So now if you want a 5 input NAND gate, all we have to do, connect 5 of them in series here, connect 5 of them in parallel here, right? So it is true for 2 input, it is true for 100 input. As long as they are in AND relation, they will appear in series in the pull down network. In the pull up network, it will be opposite. And you can test with this truth table, the basic definition of NAND gate. You will see that for every combination, it will give you the correct answer. Same thing we can do for a NOR. A NOR is A plus B whole bar, right? So they will appear in parallel in pull down network, in series with pull up network. If you now have A plus B plus C plus D whole bar, then there will be 4, there will be 4 here, right? And double check with this truth table whether for every combination it is giving you the correct NOR output. It is so. They are just a 2 simplest possible multi-value static CMOS circuit. Now this is another random example. So as you can see here, the function f it is given, it is uninverted form. So D is by itself, plus or with ABC term. Inside ABC, so I can put D between output and the ground, right? It is by itself. In parallel with the term containing ABC. Now inside the term containing ABC, B and C are in OR operation, so I put B and C in parallel. Together B plus C is in AND with A, so they are in series with A, right? So I have now the whole pull down network. Pull up will be then, first this whole D will be in series with this whole block. So I put D here, this block will be in series between D and the VDD. But inside this block, B and C will become parallel to A, because B and C are in series with A here, right? But the output that I am getting is actually the inversion of the whole function, so I am getting F bar here. So I have to put an inverter here to make it F, right? If the function itself given as an F bar as a question, then you don't have to do anything, because that is what you will be getting, right? So just randomly write any logic function, try to simplify it, and try to implement its static version and count the transistor number. Do not double count, even in input signal needs to be inverted, right?
So just one question.
Yes.
In this last equation, we can more simplify it by
Oh,
taking
yeah.
A common and B plus B dash.
Oh
B
yeah,
inverted C.
I just, that's what I said, depending on to what level of simplification you go. Like for example here, you can basically make it A. I just gave you an example, B prime C. So then the circuit becomes even simpler.
Yeah, like this. Right?
Yeah. So that is something you can do. So keep simplifying, but if you stop here, your circuit is correct. If you go all the way down here, still your circuit is correct. If you implement this one, logically you will get the same function, but the point-wise there will be some difference. Because I will have the simplest possible answer in my hand, yes.
And just to confirm, I'm sorry, like I know y'all was counting these transitions, but you counted the B, inverted B twice.
No, once.
Okay.
Because when you need an inverted input,
Yeah.
let's say you need B bar
Right.
in 10 different places in this circuit.
Yeah.
But these A, B, C, these are inputs.
Mhm.
It's just one single input. And wherever you need, you just draw a connection over there. So you are not inverting it 10 times.
Right.
You are taking the connection from B bar 10 times wherever needed.
Now, did we count the ones for A as well?
No, because nowhere in the circuit A appears as inverted. Nowhere in the circuit C appears as
So
inverted.
did it not get inverted at the top
No,
where you flip? So they didn't.
no. Input A remains input A here. Transistors get inverted. Connections get inverted, right? Series becomes parallel, parallel becomes series, NMOS becomes PMOS.
Mhm.
But signal, input signal, we keep it as it is.
Okay,
We don't
gotcha.
invert it.
Okay.
This last thing.
Yes.
So for B, we will be considering only for inverter, we will be
Only
considering
two
transistor,
transistors.
not for the upper one.
No, because it's from same
Same
place, all the connections are going. It is not that I'm actually putting an inverter here
Yeah.
and putting an inverter here, right? So inputs are, let's say in this circuit, it is a 4-input circuit, A, B, C, D, right? And nowhere in this circuit I need any inverted signal. So there will be just 4 input connections, A, B, C, D, and I need D twice, I need A twice, B twice, C twice. So there will be 2 connections going here and here, right?
So you said that B is independent, you can keep it between the ground.
Yeah. So no, here there is no option. Between output and the ground, D will appear in parallel to this block. But over there, that's what I'm saying, in the later part of this lecture, you will see placing D here or here above this, flipping their relative position with this one and this one will make a difference. So now when you actually go to a complex logic circuit, so I'm continuing with the same example, how to basically sequentially, step by step construct complex circuit. So what we do, we first look at the complex logic function. We identify each block. Here, so what I did first, I'm calling it my signal network 1, D. ABC together, signal network 2. So here, signal network 1 appears parallel to signal network 2. Inside signal network 2, I have 3 and 4 in series. Inside 3, I have B and C in parallel. So you basically, the other approach is first attack the individual one. So I know that D is in parallel with everything, let's put it here. Now inside the complex one, always look at the nested, the one inside bracket B plus C. Put them in parallel or in series in whatever format they are, and then look at its relation to the other one. Here it is in series. So you basically kind of divide and conquer. You look at each component, determine their parallel series relation, and go deep inside each component. Are there more than one terms, and how those terms are related, and inside each terms are there more than one variables like B plus C, how they are related. Yes.
So we need to start from inside, then go out, out, out.
It the way you feel comfortable. There is no prescribed. First try to look at the overall picture. How many bigger terms are there in series and parallel, and then I go deep inside each term to see how many smaller term and variable and how they are interconnected. Yes, you have a question? No? Okay. So this is the F bar we actually implemented, right? Not F, complete logic gate. So, what are the advantages of this CMOS logic circuit? It's actually the repetition of the same what we have discussed in inverter. It is able to produce full rail-to-rail voltage, binary 0 all the way to the ground, binary high all the way to VDD. So it will give us very high noise margin. The logic levels here now, logic levels here are not, is a ratio less design, because the logic level here at the output will not depend on their individual and relative size. The sizes will affect the resistance, it will affect the timing to produce high to low and low to high transition, propagation delay, but no matter what is the delay, they will be able to produce binary 1 and binary 0, so it is called ratio less design. And in this circuit, the way this static CMOS circuit is designed, either pull down network on or pull up network on. But for a complex circuit like this, how many possible direct paths from output to the ground? 1, 2, 3 different paths. For certain input combination, if any of this path is on, the entire pull-up path will be off. Similarly, here it can have one path, 2 paths to VDD. For a certain input combination, if any of these 2 paths is on, every path in this pull-down network will be off. Because by definition, in a logic circuit, pull-down and pull-up network will never be on together. You cannot have a connection to output simultaneously from ground and supply other than the dynamic transition time. So that is the CMOS circuit. So always, now that means during the steady state condition of this logic circuit, the output will always have either a connection to VDD or a connection to ground, not both. That gives it very high endurance. Also, it gives a very, very strong value. It is very robust to noise. And because also this existence of connection, short circuit between supply to output or ground to output, if you look from the output side into the circuit, you will see that the circuit will represent a very low output impedance. On the other hand, the input signals are always applied to the gate terminal of the transistor. Input signals are always connected to the gate terminals of the transistor, and gate terminals are always insulated from the transistor by silicon dioxide. So if you look from any input into the circuit, you will see a very high input impedance, and both low output impedance and high input impedance are beneficial property for any logic circuit. At steady state, output can only have connection to VDD or ground, but VDD and ground itself, they will be disconnected. Why? Either pull down is off or pull up is off. Between them, there is no direct connection. So ideally, due to the absence of a direct path between supply to ground, it will not consume any power consumption in steady state. So ideally, CMOS circuit consumes zero static power, except some delays. Propagation delay of this circuit, any of this circuit, will be a function of the load capacitance plus the equivalent on resistance of whichever transistors are on. So the propagation delay are functions of the transistor resistance and load capacitance. Yes.
So, as previously I remember in my bachelor, so we also need to connect with we need to draw the load capacitance, so see how many capacitors are there, then we need to calculate the delay.
When it comes to delay, you have to know actual capacitance. So here, like for example, in this complex circuit, when we are talking about output capacitance, it is the result of all the capacitance contributed by every transistor connected to this output node, plus the capacitance contributed by the wire that is connected to the output node. So this load capacitance is a result of many smaller contribution from all the different transistors and the wires that doesn't connect to the node. Yes, you're correct. To estimate the delay, we have to know the actual capacitance.
How many capacitors are there?
How many capacitances are there? So, and typically for hand calculation, it is very difficult to do that. But any circuit simulation, they have built-in model. Whenever you put the transistor dimension, the built-in model inside the simulation tool will automatically calculate every single parasitic capacitance that is connected to each node.
So do we need to calculate the capacitance?
We at this level, we will do some rudimentary calculation of capacitance based on the formula we have presented in lecture 3 and 2. But definitely, I will not ask you to calculate, because every internal node will have capacitance. Because as you can see, in this node there is 1 transistor, 2 transistor, 3 transistor connected, and each one of these transistor has lots of internal device capacitance. So this node will see those capacitance. So this node will have an internal node capacitance.
3, like 3 or 4.
We'll say 1 contributed by 3, right? So, and you have to do very complex device analysis to do this calculation, but if you need to consider those internal node capacitance in any calculation, those will be given to you.
Okay.
Because calculating those capacitance is like solving at least a factor of 10 to 20 differential equation. So, since the rise and fall time are functions of load capacitance and the resistance, we can play with the load capacity and resistance value to make the delay and rise time and fall time comparable and symmetrical. With some sizing optimization, we can get comparable rise time and fall time, comparable delay. So these are all beneficial properties of CMOS circuit. Yes, up now, any confusion up to this slide? Yes.
I have drawn it. I want to show it to you. What I have drawn, this exact same circuit.
So you have drawn kind of a different orientation.
No, but I added more. But you are saying it has 14. By my calculation, it's 3 more or 2 more came out.
If you implement this one.
This one, yeah, this one.
Okay, I want to see that. Probably you are double counting or triple counting.
Or I'm adding more. I don't know.
No, don't add more. So I can definitely stop by. I can definitely see where you are making
The mistake, yes.
If you have more than 14 for that implementation,
I'm wrong.
and somewhere you are double counting. So once again, please spend a lot of time on lecture 2 and 3. Because the contents we are going to present from here on will need you to utilize the concept and knowledge you earn in 2 and 3, right? So please go to that. So next Thursday, only 2 days, 48 hours from now, we will have a quiz on that. Okay?
This Thursday.
This Thursday.
This Thursday.
Yes.
This is just one of the 2 quizzes you're doing, right?
Okay, so if you want, I can push it to Tuesday.
Because we have to have another.
Huh? No, because right now I am actually pushing back the midterm because I have to check my travel schedule. So let's do the quiz 3 on Tuesday because lecture 3 is important. I want you to spend the whole weekend on lecture 3.
Yeah.
Forget about having fun.
It's fine not to have. It's fine by me, but the problem is next Thursday will be like too much short time for us.
And then there's all the other classes.
Tuesday I'm going to Nebraska.
So you are, that training, how many of you from this class? What time you are leaving?
I'm leaving on Sunday. I'm coming on Wednesday.
Well, we can do an alternative arrangement for you.
So you change the quiz to Tuesday? Oh, okay. And you gonna be out?
Tomorrow I will be here, so let's do that. So tomorrow. 1 and 4. Yeah.